So let's move on to the next part of the in-person presentation for the workshop now. So next we have an interesting use case where industry works closely with academia to come up with some APIs and solutions. So we're going to start out first with a talk by National Instruments and especially Charles Schroeder, who is a visionary combining both future forward-looking R&D pipelines with more product pipelines that are in the near term. And joining him will be Vincent from Europe, as well as following this presentation by NI, we'll also have a talk by MITRE Corporation, and Curtis will be presenting his thoughts on RF data sets. So Charles, please.
Kaushik, thank you very much for inviting me today. I have a chance to talk to everybody. Important. All right, so just real quick, I want to leave most of the time for the demonstration that we have. We have a technical demonstration of the use of capturing data for training a system that can recognize CBRS data. If you're not familiar with our company, we're generally thought of as a test and measurement company, but really we're in the business of helping accelerate science and engineering. Our work in wireless really goes back to just to show you the breadth of what we do, but it's hardware and software that has been critical in cellular wireless development for many years, from the very first millimeter wave experiments in 5G to the very first massive MIMO experiments in 5G, to even the RF and the software-defined radios that are the heart of the Coliseum system here at Northeastern. We've been very involved in 5G research. So anything that we can do as a company to accelerate productivity, innovation, and discovery of scientists and engineers is in scope for what we do, and you will see a lot of our hardware and software in the demo a little bit later on. When it comes to the future of wireless, and I'm just going to use 6G potentially as a rough model of the future of wireless, there's a lot of areas that we are interested in, we are pursuing right now. Some of the ones most relevant to this workshop are the area of artificial intelligence and machine learning. And for us, there's a big overlap between that, wireless communications for sure, but also in the integrated communication and sensing work. We've already heard there's some radar work being done today. We've seen some fusion from NIST on that area, and so we'll be following that very carefully, as well as spectrum efficiency and spectrum sharing, which we believe is also very related to AI and ML. When it comes to where to apply AI and ML, we are a commercial company, so we don't look at things from a science perspective. We look at it from a commercialization perspective, and this might be a little bit controversial to an academic audience, but the first thing we ask is why and where, because in general, in a commercial world, if you can implement something with a classical algorithm, it is viewed as a safer, more known answer to the problem than an AI and ML algorithm, where you cannot classically define either the input space, which is infinite, nor do you understand what a trained system will do. And as a father, I think about all the training I've done for my teenagers, and yet I can't predict what they will do when I put them out in the wild. And there certainly is, with the newness of artificial intelligence and machine learning, we need to understand the benefits that we're trying to derive from a system where we're using artificial intelligence and machine learning, and not just, hey, it's cool to do so, and we can, therefore let's try. So the 3GPP has recently started a working group on the use of artificial intelligence and machine learning at the RF and the PHY, so lower levels in the stack. And while we've seen a decent amount of use sort of at the network layer in the past, we're seeing really growing interest on the lower layers of that stack. Now, one of the interesting things about that is at those layers of the stack, you really do need the IQ samples that we have talked about earlier today. You just can't do some of these things without them, but there are a set of concerns and challenges that go with them. At the RF level, we're seeing a lot of interest in the use of programming what are becoming very, very complex RF signal chains and front ends, and that can be the configuration of the hardware itself, or it can be the configuration of things like digital predistortion algorithms or signal correction algorithms that exist actually in the hardware portion of the signal chain. And we're seeing that not just in academia, but we're actually seeing that begin to really grow in commercial use. As the number of standards and bands and tunable settings within the RF hardware to make them work in all the chains gets so complex, it literally becomes a manual task of months to come up with an optimal configuration of hardware for any given setting And that is the reason why people would consider AI and ML to do that. And then above that level, in the PHI, we see channel estimation, symbol detection, these areas growing in interest. And so we're very, very interested in the IQ sets that it would take to do that, of course, in a responsible way that preserves privacy. When we talk a lot about communications, there's also a lot of interest in the defense area as well. I think a lot of us are familiar with some of the RF fingerprinting work that's gone on here at Northeastern that came out of some of the original DARPA RIF-MIL contracts in that area. So we want to, from a defense side, we want to be able to detect signals in the world, to be able to understand what's happening, and then eventually, in sort of an EW sense, to potentially do something about it. And we've already heard from NADA at NIST this morning how they've taken some radar signals, but they can't release that data because then that data contains a set of information that people do not want to be public. And so if we move on from there, where should this data come from, and how do we get access to more of it? I do a lot, not just in the RF space, but also with our transportation companies who have spent the better part of a decade looking at training the ADAS systems that will eventually be the precursors to autonomous driving. And they have been using a lot of artificial intelligence and machine learning data for years. And within that community, there are really two camps and philosophies. There's one camp, which I'll call the mobile eye camp, which is you absolutely have to have real-world data. There are nuances in real-world data that you cannot reproduce with synthetic data, that you will never be able to reproduce with synthetic data. And if you want to put a vehicle on the road that's not going to kill somebody and you're training it with artificially created data, you're taking a huge liability risk. So it's not just a privacy, or John just asked the question in the recent panel, what metrics of fidelity do you need? There's also a psychological element to that, of can I trust something that was artificially created by an algorithm? Now, the other camp, which I will call the NVIDIA camp, is no, absolutely we can use synthetic data. And in fact, synthetic data has a ton of advantages. Number one, it doesn't have a lot of these privacy concerns. Number two, I can take that data and I can take one scene and I can do it in the dark or in the snow or in the rain or in the sleet. I can create any arbitrary set of circumstances, and it's a lot more efficient to do that. And as long as my data does have some semblance or correlation to the real world, I should be fine. And what we are beginning to see in the transportation space, which I think we could apply as a corollary into the RF and wireless space, is the use of real-world data to create synthetic data. Nada mentioned scenario-based situations or scenario-based tests earlier in her talk today, and we're really seeing that as a strong thrust of influence in that area, which is what is the set of scenarios under which my algorithm needs to work, and how do I get a rich enough data set in order to be able to support that? And what the transportation world is doing is they're sending vehicles out in the world to capture those images and radar and LiDAR signals, and then they are very quickly translating the scenario into a virtual world. So therefore, they capture the events of the real world, but they turn it into synthetic data as quickly as they can, and then they can add noise or daytime or nighttime or perturbate from there. And I think there will be very interesting work to happen, both technical work and psychological and legal work to happen in our space on what should be simulation and synthetic source data, what absolutely must be real world or IQ-based sampled data, what can we get from things like channel emulators and end-to-end test beds, and what are the capabilities that we need? And so what you're going to see in the rest of the talk today is the early work that we are doing in cooperation with Northeastern and other people to begin to get systems that allow us to get these various sources of data, to bring them together, to analyze them, to pre-process them, and to make them useful. And in many ways, that starts for us with standardization. If the data is in whatever format the researcher decided to capture it in, then we will never be able to share. We have decided in collaboration with Northeastern to base the work that we've done on the SIG-MF standard, and then what is the metadata and the labeling and the tagging data that needs to go into that data to make it useful. And it is amazing how much it helps just to have a system that you know will work, as opposed to having to cobble stuff together and spending a significant portion of the budget just setting up something that can capture that data. And so with that, I will take a seat and we'll let the actual real-world system do the talking for us.
Thank you, Charles. Thank you very much. So what I'm going to do is I'm going to take this discussion one step further. I'm going to define the problem where they are going to use an API data generation tool that was designed by National Instruments, and you will see a demo for this soon after. But this discussion came out when we were talking about how hard or easy is it for, let's say, a graduate student to go in and just type out a few sentences, a few lines of code, and collect a data set with properly compliant SIGMF metadata accompanying it, and then use it for some future research. So we just took one example of the data collection for the CBRS span. You saw that discussion earlier in the day as well. So what you see here is just to define the problem. For the CBRS band defines 3 layers of access priorities. There is a general authorized access, then there is a priority access, and then there are the incumbents. An incumbent example of incumbent could be naval radar. Now, what you see on the right-hand side is just an example where imagine that you have an active LTE transmission. And within that LTE signals, and you see a spectrogram here of frequency versus time, you see a very slight embedded radar pulses. Probably you can't even see it with your naked eye, but there are these thin lines that occur at regular intervals along the y-axis, right? So that's along the time axis. So you see just very thin lines appearing. So could you use something like machine learning to identify these little radar pulses? And for that, you really need good machine learning techniques to filter out this information. So we wanted to create data sets, and we didn't know how to do that. So for that, we approached National Instruments. We said, look, here is a generic platform that we need. Right, the generic platform is what you see on the left-hand side. It must be able to support different waveforms. Yes, in this example, it is LTE and radar, but we would also want Wi-Fi and other sorts of waveforms. We should be able to pre-record these waveforms, perhaps even synthetically generate them and transmit them. It should be easy to use for a first-time user. We want to generate compliant metadata, so the system should automatically create metadata of the experiment that was run. And then we want to take this set, and we should be able to work with them in our local software-defined radios in the lab, but then take them over to, say, Colosseum and Powder, make sure that the wider community can use. So just for the use case of the CBRS, you're going to see a demo where we are able now to transmit data from an open source stack or save data from a prior experiment or synthetically generated data. This is going to be combined with radar signals. Now these radar signals are again synthetically generated. These are, and you will soon see in just a bit. And it also, the system allows you to decide how much to scan, what should your bandwidth of scanning, what should be your center frequency, whether there should be just one radio sampling versus 10 radio sampling. You can configure all that on the fly. So these APIs will be released as an open source contribution, probably already is, but will soon be, hopefully by this week or next, we should make, National Instruments will make this available outside, and you will see the use case in just a bit. So I'm going to pause here, and is Vincent online?
Yes, I'm online.
Wonderful. So if he could just move to the Zoom presentation online and allow Vincent to share. Yes, there you go. So Vincent, please feel free to share. Tell us more about these APIs and how you are creating this and how a user will be able to use it at the end, and then we'll see a demo.
All right. Can you see my screen?
Yes.
All right. So it's also for me a great pleasure to have the opportunity to talk about our new data collection API that we developed together with Kaushik and his team with the goal to streamline the creation of data sets for the RF wireless community. And this presentation will just be a very brief overview before we will see a demonstration from Kaushik's team, how this data collection API is being used to collect data for this specific CBRS use case. This slide represents an overview about the workflow from a data recording perspective towards the use of the data for AI/ML model training and validation. And today we will mainly talk about the data collection API, which is used to automatically configure a certain recording setup and capture data, format it, and store it in a database. And for this specific work, we decided together with NU to use the ZigMF data format because of its openness and readability, because this is where we think it's really important that the data sets itself get adopted by a greater community. But there's also a second important API as part of the system, which is used to create specific training and validation data sets out of a bigger data library. And such big data libraries can contain terabytes of data coming from different sources, such as recorded data, like with using this data collection API, but also data sets from simulation tools, so that one can create data sets with combined simulation and recorded data, which has been also discussed earlier today. Therefore, it's important to provide data management tools that make those data usable for different AI/ML application use cases. So this also underpins the importance of a common data format, such as ZigMF, to broaden the use of those data sets, in particular if such pre-processing APIs contain different means to pre-process the data to bring it into a shape so that it gets usable for dedicated training and validation tasks. And here on the slide, we show a specific recording setup for the CBRS use case using a number of parallel transmitters that transmit different waveforms in parallel and one receiver station that captures the overlaying signal. And the Northeastern team will show a live demo in a couple of minutes. But the data collection API is not restricted to this specific application, but it's already more flexible for other use cases as well. And this is captured here on the current slide. But the key advantage is actually that one can configure a complete recording campaign in a JSON file, where each transmitter and receiver can be configured with completely independent parameters, such as carrier frequency, bandwidth, TX, RX gains, and so on. And these parameters can be specified as single values or list of values or even a range of values. And for each transmitter, one can specify an independent waveform, which is important, in particular for the CBRS use case. And these kind of waveforms are then continuously transmitted. And for these waveforms, we support already our TDMS format, but also you can download also already MATLAB files or other formats. So it's quite flexible in this way. Also, the number of transmitters and receivers is scalable to any number that the network of user Ps in your testbed supports. And this is in particular important if you want to use this API in testbed-like environments with multiple user Ps that act as transmitters and receivers. And with that, you can really do some scalable kind of data recordings. And the configuration of this JSON file that you see here on the right-hand side of this slide is actually the key work that one has to do to prepare a certain recording campaign. And afterwards, the API runs automatically through all possible parameter combinations and creates a predefined number of data recordings, which will be automatically saved in the ZigMF format, which with the corresponding configuration parameters stored as the metadata. And this, from our viewpoint, can simplify bigger recording campaigns significantly because the output is ZigMF, and the use of those data sets for subsequent AI/ML training is simplified in this way, because all the information about the receiver and the active transmitter stations are captured in the metadata, and one can filter afterwards for specific recording configurations. And this is my last slide, just showing an example generated ZigMF meta file. So if you're familiar with ZigMF, on the top, you have these kind of common core namespaces with the global parameters and the capture parameters. We treat these parameters to describe the RX waveform capture. So the ARC station, if you want. And I think an extension that we proposed here is that in these kind of annotations field, we have specific fields for each active transmitter that describes the signal that has been basically transmitted. And as as we mentioned, so I think for the C++ use case, we transmit several signals in parallel, like LTE and a radar waveform. And for that, I think if you want to use these data for an AI/ML training, then you can basically just filter them and also know all of these kind of active transmitters already and can incorporate that into the pre-processing of the data sets as well. All right, this brings me actually to the end of my presentation. Now I would like to hand over to the team of Northeastern to show the live demo.
Okay, hello everyone, good morning. My name is Chinenye Tassie, and I'm a PhD student here at Northeastern in Professor Charles Schroeder's lab. So today I will be demonstrating the National Instruments Data Collection API that you've just heard about. Okay, so let's get started. Okay, so I'm currently within the API. I'm just going to kind of take you around and show you what we have here. So the API provides a configuration file which you would need to set specific parameters that you want to use for your data collection. So I'm just going to show you our configuration file, which is this one. So for this setup, I have 3 X310 USRPs, 2 will be transmitting, and 1 will be a receiver. One of the transmitters will be transmitting LTE, and the other will be transmitting radar. And it's over a wired connection. So you can see that here, USRP1, this is a transmitter. You can see that we are using a frequency of 3.6 mega, 7.68 megahertz sampling rate. We will be transmitting a 5 megahertz LTE waveform that was provided by National Instruments. And likewise, we also have another transmitter that will be transmitting another waveform that is a radar waveform that was also provided by National Instruments. And then we have a receiver, which will have a sampling rate and bandwidth of 50 megahertz. And it's important to note that for this data collection, we want to collect non-overlapping signals, so we're using different center frequencies. And this is for the CBRS use case, so we are using the 3.6 gigahertz frequencies. And at the bottom here, this specifies like where your files will be saved, so there's like a directory. And of course, we'll be collecting SIGMF data format. We'll be collecting 10 snapshots, so 10 recordings, and the TX execution is set to parallel because both transmitters will be transmitting in parallel. So we're just going to save this. And now I am going to run the main API data collection script. So it's starting up. You can see the different configuration parameters for the different radios. So everything looks good, no warnings, no errors, and it started the data collection process. So you can see that there are 10 frames from 0 to 9. So just to confirm that all the frames were properly collected, I am going to go to the location where I configured the data to go. Just gonna, and you can see that we have the files that were collected. So next, I am going to SCP this folder over to Jerry, who will demonstrate the machine learning classification part of this demonstration. Yes, but before that, I am going to show you that the signals we collected, how they look and that they actually look good. So I'm gonna copy that. And here we have a MATLAB script that will plot PSD plots and spectrogram plots of the collected data. I'm just going to run this. And as you can see, we have, very clean signals over here. You can see in the spectrogram, the LTE is clearly visible, and you can see the radar. And likewise, in the PSD plots, the powers are equal and everything looks good. So now for the SCP portion to the machine learning classification algorithms. Yep, okay, so the files have been transferred, and Jerry will take over the rest of the demonstration. Thank you.
All right. Hello, everyone. My name is Jerry Gu. I'm also a PhD student here at Northeastern, working in Dr. Chowdhury's lab. I'll be demonstrating the machine learning pipeline. So to look at which screen, okay. All right, so first I'll be obviously logging into my account. Oh, okay, thank you. Okay, so now I'll explain a little bit about what the pipeline does. So we have a trained model which takes in, for example, the collected signals that Chinenye just transferred onto my file or my account. And what it will do is, for each file, it will output the prediction of whether or not it is a LTE signal, a radar signal, or a file that contains both signals. Just to show that the files were transmitted and what files we have, we prepared two folders, one which is one which contains pre-captured files that we've loaded onto this account. If I can just show that. All right. So what we have here is we have 9 files. They are either, again, they contain either a radar signal, a LTE signal, or both types of signals. So I'll exit back out. Okay, and the other folder, which contains all of the signals that Chinenye just transferred onto my account. These were the live captured or live recorded signals. I'll do a quick bit of configuration, just removing some of the metadata files that are in this. Okay, and now the metadata files are removed. So now I'll move on to the demonstration of the pipeline. Okay, so I'm going to run the pipeline with the pre-recorded files first. Okay, so what it'll show is first some configuration files, the model that we're using, and then at the very bottom you can see that the model is being tested. There's a sort of loading bar, and then it'll output one of the 3 prediction with one of the 3 types of signals. Each inference, as of right now, should take around 20 seconds, so we'll just give it some time to process. Okay, so as you can see, currently the pipeline will give you the name of the file. First, in this case, we can see that this file is a radar, it contains a radar signal, and the prediction, which is also radar. So in this case, the pipeline predicted accurately, And with the second prediction, we can also see that, oh wow, it's moving quickly. We can also see that it's also giving us the correct prediction of having both signals. I'm going to stop this early. Okay. And now we're going to run the other pipeline. Captured. Okay. Now, it's important to remember that the signals that Sinead transferred onto this account were files that contain both signals. So if this is working properly, it will give the prediction of both signals. So let's see what the predictions are. Sometimes it takes a little bit of time, but okay. Ooh, okay, so in this case, it actually gave us a prediction of LTE. Sometimes this happens. The accuracy of the model is around 95%, so we got a little bit unlucky here, but let's just see what happens with the next file. Oh, okay. Okay, so it seems that with these two predictions, perhaps the signals that were recorded in this auditorium, the setup might be a little bit different, even though it's a wired connection. Let's give one more chance. Okay, so I think it's going to just give us LTE signals, in which case we'll have to look into what the setup is doing, but it should give us, in a sort of in another live scenario, it should give us predictions of both signals since both the transmitters are on. I'm going to stop it here early. Okay. And with that, hopefully we can get this issue fixed, but that's the demonstration of the machine learning pipeline. Thank you.
Thank you. So just wanted to say thank you to Jerry, Chinenye, the team, Winnie, Debashri, and also Vincent, Vincent and Abdo on the other side. They've been, I think, great collaborators, and I think it was a joint team effort. So I think the takeaway message is that you saw how easy it was to generate data. It was just a few clicks, and anybody could do it, right? And that's really what we want to enable as one of the APIs that we want to release very soon as part of the RFDataFactory. So we are running a little bit behind time, but I hope you won't mind if we eat a little bit into the lunch break. But because we have a very interesting presentation by Curtis following this. And so Curtis, if you can please come up. We'll probably shift this about 15 minutes down and make a...
Sure, thank you. All right. Well, yes, as Kotzch said, I have the luxury of being the roadblock to lunch. So my name is Curtis Watson. I'm with the MITRE Corporation. For those that are unfamiliar with us, we're a not-for-profit that manages several federally funded research and development centers. We straddle industry, commercial, government, and academia, so it's always great to have opportunities to talk with Kotzch and present to a crowd here. Today I'm going to talk about a hierarchical schema that my team developed to describe radio frequency signals, and this was in support of a current ongoing IARPA program called Scissors, which is basically trying to detect anomalous signals in the ambient background. So, to set the stage with a little bit of a cartoon figure, but just lay out the challenges that was presented to us, because there was kind of multi-interests or competing interests in what we were trying to develop, because we wanted to have overall a single architectural schema, but there was performers that will be developing algorithms that need to report activity in the background. We as the T&E team have to orchestrate and coordinate all the transmissions that are going on. And then there's, again, we want to have this not just be something that's living in simulation or emulation. We actually are building a physical test bed, so we have to deal with all the challenges of just operating in the natural ambient background. And so just kind of pictorially just showing you the variety of signals that, you know, one might expect, again, cartoonish, but the point remains that there's persistent signals, there's signals that are bursty in nature, but maybe on a single carrier, frequency hoppers, and then of course, signals that might be hiding under the noise floor. And so as we try to describe all these communication signals that might exploit these various dimensions of freedom to actually transmit the information, you know, the thing that we observed, or the challenge that we had, was we couldn't come up with a single annotation or you know, a flat layer annotation to describe all the interested waveforms that we might generate. You know, again, it gets back to, and the perfect example for a lot of our thought experiments is the frequency hopper. You know, showing a simple bounding box here of this example that I have does do a good job pictorially, and maybe even for some of the untrained folks that might leverage data sets, you know, gives you a good sense of where it is. But when you think about algorithms that might use that information, or especially machine learning, you know, that signal, that bounding box, actually the amount of energy is very small relative to just the background energy. So depending on what you're doing, I mean, if you're just trying to discriminate a frequency hopper versus a persistent signal, yeah, that's probably good, because your algorithm would pick up on maybe percentages of energy. But if you're actually trying to dig in and characterize the signal attributes, modulation, you know, duty cycle, bandwidth of the individual hops, you need that extra level of granularity of reporting. And what we came up with is a tiered multi-level hierarchical description. So again, keeping with cartoons, the way I would like to describe this is first come top down, and then kind of go back bottom up, and try to convince ourselves that we came up with something useful. And so showing what we're dealing with is a source that transmits something. And so that source is transmitting a signal instance that is made up of RF energy. And so that's kind of how we broke down our three levels, is we have a source that has signal characteristics, which is made up of energy. And kind of showing in the time frequency plane here, what we mean by that is, again, you know, the orange transmitter has an activity of RF transmissions, and those kind of cluster together to be a single signal instance. And it can happen multiple times over the duration of a test scenario, or just, you know, naturally occurring. And so now you can have multiple devices transmitting, whether they're SDRs, cell towers, you know, IoT devices, and we can kind of break down our characterization of what's going on in you know, a large swath of spectrum. And so again, you know, at the very top level, we're just talking, you know, create a device ID essentially for the source. This might enable RF fingerprinting, discrimination algorithms, but really a lot of, at least in my mind, some of the interesting detail comes into the middle layer, which is the signal reporting, where now we're starting to ask you to tell us, you know, where is it in time and frequency. And again, it's kind of at that large scale bounding box, but then also what's the protocol, what's the modulation, modality, meaning, you know, is it frequency agile, is it spread spectrum, single carrier, things of that nature. And then, you know, some diagnostic or debug information about what was your tuning frequency, sample rates, estimated SNR, things of that nature. But really, the core of it then becomes this reference pointer, or a collection of the RF energy, which is at the very bottom. You know, again, we're just basically taking bounding boxes. And while, you know, this isn't necessarily a computer vision centric approach, we definitely had reasons for going with more of a bounding box mentality versus, say, center frequency and bandwidth. And part of that, I guess, I'll get to that on the next slide, but you know, so again, that's kind of our top down, and the motivation on that, once more, is that we have to orchestrate some of these signal activities. We're going to be standing up a bunch of frequency hoppers, or LTE, or, you know, emulate some LTE or LoRa type devices. And so from an orchestration perspective, it made a lot of sense to go top down. And actually, one thing I'm not showing here, which could talk offline, is there's kind of a parallel schema that we developed for orchestration itself, because then you can start to think of, your devices as actors in a play, and you're creating scenes, and they got different roles to do, and are they on script, off script, things like that. So that's a whole side conversation by itself. The last point I wanted to make on this slide is, then kind of going bottom up, because as a performer on this program, the people making algorithms, that's probably where they're going to be starting is they detect the energy. Okay, where is it? What does that mean? So you might start to aggregate a bunch of energy, and then you start to piece it together and say, oh, okay, that's a Bluetooth transmission. So now you can start to characterize the signal. And then, okay, after time, you start to observe multiple bursts of Bluetooth activity, and you kind of collapse that together as a source. So again, the thinking here is that we wanted to, again, pound it home, be able to orchestrate so that we have some amount of ground truth, so that then as the algorithms spit out reports, we can compare and evaluate those answers. So actually, I should help with the time because, the one thing, this might get off the slide stage, basically, the one thing I wanted to foot stomp is that, again, from the orientation of being able to orchestrate but compare results, we feel like this helped us be able to describe what we're going on. And while our motivation was, actual transmissions, collect it and report against it, it certainly can be used for synthesizing or generating data sets. And, then now you can annotate lab or field collects using this type of schema. And again, the key benefits, and part of this we somewhat observed from the DARPA RIFMOS program when that was going on was, again, just think about a frequency hopper, for example. It's a great thought experiment example. If you just put a box around that and then you try to train on that, you're getting a lot of noise in there. You're getting a lot of nuisance parameters in that data. And now if you throw it to a machine learning, especially machine learning, where it's basically just taking what you give it and it's trusting you 100% that that's great data, you could get some inaccurate models, or rather it'll learn behaviors that may not translate when you go to another setting. And so we wanted this granularity of the multiple tiers, and so definitely think we achieved that. Obviously, a challenge with this schema, which might be a challenge with any kind of schema, is how do you handle waveforms that are changing? Anytime you mark down and say, hey, this is what I think the attribute of the features are, well, now you're kind of stuck with that. And so, adaptive modulations is certainly a challenge with this schema. I will say we did incorporate the ability to attach belief vectors basically to your labeling, so you could actually assign multiple values and have kind of weightings or likelihoods, however you want to characterize it. But that was one thing. The other thing, I guess, back to the bounding box, one of the reasons we chose the bounding box is that now you have to start, well, rather, if you take a center frequency and bandwidth approach, now you have to get very precise in what bandwidth means. And while, from a very textbook perspective, that might be clear cut, but when you're trying to make these data sets, we almost took the approach of you know it when you see it type thing. Because again, if these are being fed to algorithms, if there's an Internet of Things device that doesn't have a spectral containment filter on it, and you get all these side lobes that go out very far in frequency, well, we don't really want to put a bounding box on that whole span. We really want to capture where the core of the energy is. And then similarly, from orchestration perspective, we know what we told the symbol rate of a PSK modulated symbol is, so we can translate that to a rough order of what the bandwidth is. And so we felt that bounding box approach allowed us to have a little bit more flexibility, and then of course opportunity for creativity for someone smarter than myself to improve this schema. So I think with that, I think that was my last slide. I certainly be welcome any questions. I guess I probably should have said this up front. All these opinions are my own, not necessarily intended to convey a position by MITRE or the U.S. government.
Thank you.
Like,
So, maybe just hang on for a minute, we have some questions for you. Maybe, yes. Do you want to speak to the mic? Is the mic there?
Sorry, I apologize. I didn't understand what problem the schema is trying to solve.
Sure. Let's see if I can go back. Yeah, the problem that we were working is this IARPA program called SCISSORS. Stands for Support Securing Compartmented Information with Smart Radios. But basically the idea is think of possibly bugs in a secure space, whether it's a DoD installation or you could imagine business espionage where signals are trying to exfil out information, steal secrets type of things. And so we would need capability to develop algorithms that can report the baseline activity, but then start to also report when anomalous activities come. So the challenge that we were coming up with was making a reporting mechanism so that they can essentially annotate the real, near real-time annotation of what's going on in 6 gigahertz of spectrum, let's just say. And so the problem came from we needed the performers that are making algorithms to have a method to report what they're observing. But the natural, I guess, benefit is that we could also use that for annotating any data collection that we might have.
So it's like a uniform nomenclature, like everybody, how do we name everything?
Yeah.
And then in this case, so some of the challenges you mentioned relate to adaptiveness of things, frequency hopping or temporal changes. So the time axis doesn't figure in this, or every name is at time t equal to t
So
naught.
yeah, I mean, and again, I guess the cartoon is useful here, and with the frequency hopper itself is the reason we went towards a hierarchical description is, if we have the bounding box that's being displayed here on this frequency hopper, that's our signal report. And so you still are saying where that burst of signal activity is occurring. But I didn't put it on here because it get crowded, but you would actually also put bounding boxes around each individual hop that you detect or estimate. And so it's the combination of those two allows us to have some sense whether or not you detected and reported that. And again, ARP is reporting this. But if you built this data set, you could do that where you could provide all the individual hops where they are in time and frequency, and maybe that's useful if you're trying to do a modulation classifier or whatnot. But the higher level kind of lets you know just where the signal is if that's all you're interested in.
Thank you.
Yeah.
Any other questions? Questions from the audience? Questions from the audience for Curtis, or we can also go back to questions to National Instruments if needed.
Hi, Curtis. Thanks for your talk. I'm Nick Lanneman from Notre Dame. And my question, maybe a concern, is what happens if we have too many schemas and the schemas are, inconsistent or hard to translate between them? Is there one schema that can rule them all here?
Yeah, I mean, well, I guess we'll solve that in this workshop here maybe, but the point is well taken. I mean, I guess the previous talk we heard from SIGMF, and I know that has, a large backing, and so certainly, if this was ever to become part of the community, we'd want to try to mash it up with SIGMF. And we did look at it, when we first started the problem or this challenge. I mean, it's like anything, as engineers, at some point we just had to decide what to do, and we couldn't figure out at that time a couple years ago how to modify SIGMF in an easy way to accommodate what we're trying. Now, what I saw that Northeastern doing, maybe it's worth a revisit. But you're right. I mean, at some point, we as a community need to kind of just decide what it is and improve it as it goes. But yeah.
Thanks. Actually, this is more of a question for the previous presentation on CBRS. So, so it looks like what you're developing for the CBRS example in particular is all in emulation or simulation. You're generating a signal according to an LTE specification and transmitting it, and a radar signal and transmitting it and receiving it, and then trying to. Is there a way for, say, if I go out and, you know, I have captures of CBRS signals in the wild, so to speak, from a real CBRS transmitter, how does that feed into this platform that you have? Or how can it feed into the platform?
So I'm happy to take the first, maybe a two-sentence answer. And Vincent, if you're still there online, feel free to jump in. So the system allows you to capture waveforms, save them as IQ files, and then retransmit them at specific time instances of your choosing. So you could capture traces and retransmit those traces. That's something that can be done. But I'm going to let Vincent give you a more authoritative answer on the, if I missed something out.
Yes, thanks. So maybe important to mention is that the transmit and receiver part of the API can be separated. So what you could do is you could generate some CBRS kind of use cases with parallel 4G, 5G signals together with radar signals to train and to train your AI/ML algorithm. And then I think afterwards you can just capture then some data from a live kind of network and then make some inference or whatever. So if you know basically a certain scenario where radar and an LTE signal, for example, is transmitted, so it's certainly possible to feed in actual real data recordings.
Any other questions before we break for lunch? Well, if not, I would like to thank the speakers in the previous panel. Thank you, Curtis, Vincent, Charles, and the many students who presented. Thank you very much. We'll meet back here again at, I believe, 1:10, and we will resume the program from there on. So thank you again. Please disconnect, have a little bit of lunch, and keep thinking. We have some great discussions and small group breakout sessions just following this.